Hello and welcome to our lesson on fundamental trigonometric identities, or just fundamental trig identities. What we're going to be transitioning to in this module is back to our algebra, basically. So the first part of our course, like first 60% of it, we focused on algebra, and then we took a little break with module 6 and looked at trig, and now we're going to, in this unit, put those two things back together. So we had to talk about the basics of trig before we could get to where we use the algebra, which is for solving trig equations, for verifying trig identities. So we need processes like factoring and isolating variables. Okay, the two of these things are now going to merge. So the algebra is going to come back into the trig. Okay, so trig identities, first of all, those are just statements of equality. So they're statements that say that one thing is equal to another, and in this particular case, it's one trig function is equal to a version of another. And the reason we need these is so that we can make substitutions for terms in an expression or for terms in an equation. So we use these to make substitutions. Okay, and these identities, along with, again, algebraic solving methods like factoring or like isolating variables, where we subtract 2 from both sides, divide both sides by 3, these kinds of basic algebra things. Those are not only going to be useful, but they're going to be necessary in simplifying simplifying trig expressions. That's something that we'll do. Also in verifying trig identities, that's something that we'll do. And those two things actually we will look at today. And then eventually for solving trig equations. Okay, so we got to be able to factor, we got to be able to solve using solving strategies, we have to be able to add and subtract fractions, and they don't have to be just normal fractions like our rational expressions, getting common denominators. All these skills that we talked about in algebra, they're coming into play. Okay, now the trig identities that we're going to start with are what we call the fundamental identities. Some of these we've talked about, some of them we've talked about explicitly, some of them I've sort of alluded to but not actually put down formally, and then a couple of them are going to be new, but hopefully all of them will make a little bit of sense. And these aren't things that you would be expected to memorize. I would say a few of them, like these reciprocal identities, these we should know. The quotient identities, these we should know. And these Pythagorean identities, these are going to be introduced for the first time today, but they're commonly used. I would say committing those few to memory is probably going to be helpful. The rest of them, as long as you have a reference sheet and you can use them, you're going to be fine. Okay, so the reciprocal identities, these are the ones we talked about specifically in the last unit. We said that cosecant was the reciprocal of sine. We said secant was the reciprocal of cosine. And so then the reverse of those would be true. Cosine's the reciprocal of secant, sine's the reciprocal of cosecant. And then we said cotangent was the reciprocal of tangent, so then tangent would have to be the reciprocal of cotangent. Okay, so those we've talked about. These guys over here, these cofunction identities, these are just transformations of our parent function. So let's just look at, for example, what the first one is saying. So let me get rid of this. Cosine of x, we know what this function looks like. If we're to graph the parent cosine function, trig, then we're going to see a graph that starts at its maximum there, and then, let me go ahead and fix this. Let's go from 0, oh man, come on, my fat fingers. Let's go from 0 to 2 pi, let's go by pi over 2 units, and let's go from, let's say, -2 to 2, so we get a nice good picture here. And okay, so there's basically what our parent cosine curve looks like over the interval from 0 to 2 pi. Now what that's saying, or what this first identity is saying, is if we took the sine curve, so let's put the sine curve in here, sine of x, we know it's not the same function, but if we were to shift it pi over 2 units, then it lands right on top of the cosine function. So if we shift it over, it's the same function. So the sine curve shifted over by pi over 2 units is the cosine curve, right? And basically what's happening in these is the same. If we were to shift any of our trig functions by pi over 2 units, we're going to end up with its counterpart. So sine lands on cosine, cosine lands on sine, or tangent lands on cotangent, and vice versa, and secant lands on cosecant, and vice versa. And that should make sense. These two, the sine and the cosine, they had the same kind of curve, right? The periodic curve. Tangent and cotangent, those both had the branches that went up and down toward, or up forever and down forever toward infinity and negative infinity. And then secant and cosecant, both of those graphs had the parabolas. So if we just shift, they're going to map onto each other, okay? So this is basically just transformations left and right. This is transforming one function, but it's basically the same thing. So it's just another shift of the graph. So if we start with our sine curve again, there's our sine curve. These are called period identities. If we just shift the whole period, the function will land on itself. So there's our sine curve. So what this is saying, just in the first one, for instance, if we take our sine curve and we just add 2 pi to it, if we shift it over 2 pi, it's going to land on itself, okay? So the same thing all the way through, except tangent, we don't have to shift as far, and cotangent, we don't have to shift as far. Tangent, cotangent, we only have to shift pi radians for it to land on itself. Okay, so these are just transformation rules. And that's what's happening here as well. These are transformation rules. Now they're called even and odd because of certain symmetries. We say even functions are symmetric with the y-axis. We say odd functions are symmetric with the about the origin, but I'm not so concerned about those words as long as you understand what's happening in these identities. So again, if we were to look at sine of x, there it is. I'm going to leave that in there. If we were to put a negative in there with x, so the sine of a negative x, that's going to reflect our graph over the y-axis. And what that's saying is if you were to take your sine curve and reflect it over the x-axis by moving the negative to the outside, then it looks the same as when you reflect it over the y. So the sine of x with a negative out here, right, we can see, oops, I'm moving the negative in the wrong spot. So I have the green one, that's the original. Black is reflected over the y-axis, and then red is reflected over the x-axis. But the red and the black, those are the same function. Okay, so it doesn't matter if you reflect over the x or y, it's the same graph. So what this one is saying is reflecting over the y and the x, same effect. Here, reflecting over the y and the x, same effect. Here, if you just reflect over the y, then you're back to your original function. Same thing here, just reflecting over the y, you're back to your original function. And then here, if you reflect over the y or the x, those two results are the same. Okay, so these are all just transformation rules, but to help us again in the processes we're going to be looking at soon. These we've talked about in the unit circle. Remember our right triangle that we started with to build the unit circle, right triangle with a radius of 1 translating to our unit circle radius of 1, hypotenuse of 1, sorry. We said if this was a 30-degree angle, that this would be a half, and this would be radical 3 over 2. So when we go to find the sine of the angle, of the 30-degree angle, sorry, we end up with opposite over hypotenuse, so 1/2 over 1, but that's just a half. So this side here ended up being just the sine, and this one here ended up being just the cosine. So when we were looking for the tangent of our angle, normally we would take opposite over adjacent, so that ended up being sine over cosine. And so that's in general going to be true. If we're taking the tangent of an angle, that is the same thing as finding the sine and dividing it by the cosine. And then since cotangent's the reciprocal of tangent, it's cosine divided by sine. These ones are used fairly often, so again, good to probably commit those to memory. And then we have these Pythagorean identities, which come from exactly what they're saying they come from. They come from the Pythagorean theorem. So let me go back to a right triangle here for a second. If we have this, let's use the 30 again, and this was a half, and this was radical 3 over 2, and this was 1. Actually, it doesn't matter what the triangle was, right? The opposite side here ended up representing the sine, and the adjacent side, let's just call this theta, doesn't have to be 30. The adjacent side here ended up being cosine, right? So cosine of theta, and this one ended up being the sine of theta. So in the Pythagorean theorem, we would have just called this side a, this side b, and this side c. We would have said a squared plus b squared is equal to c squared. Well, in this case, we can say that cosine squared plus sine squared is equal to 1 squared. And that's where this first one comes from here. Now you notice the notation is a little different. If we are going to square cosine, we're going to square sine, we're going to square any of our trig functions, instead of having to write the parentheses here, we're going to move the square inside with the cosine, because we don't want to have to write the parentheses every time. And if we don't write the parentheses but we put the square here, it looks like we're squaring theta, but we're really squaring cosine. So in place of having to write cosine theta quantity squared, we move the square in here and say cosine squared theta like this. Okay, so that's where that first one comes from. Now, the other two Pythagorean identities come from the first one. This eraser is too small. Let me show you. So if we take this first one, sine squared x and cosine squared x equal to 1, and let's say we divided both sides, or every single term, by sine squared. If I divide everything by sine squared, that's a legal move, right? We can divide both sides of an equation by something and keep the balance of the equation. Well, this is going to reduce to 1. And then cosine over sine, we know is tangent, so we can call this tangent squared. And then 1 over sine, we know is secant, so we can call this secant squared. And so that's where this one comes from. It comes from taking this one and dividing it by sine squared. And then the last one comes from taking this first one and dividing it by cosine squared. So if I, again, take my first one, sine squared x, cosine squared x, and 1, and I divide the entire thing by a cosine squared, then sine over cosine is going to be tangent. So tangent squared. What did I do on the last one? Did I just do the same thing twice? I don't know. I'm having a moment. Sine over cosine's tangent, so tangent squared x. This is going to be 1. And then 1 over cosine is secant. Maybe I just did. That's what I feel like. That's what I did. Maybe I goofed. Okay, so sine squared, that's 1. Oh, cosine. Yeah, I did goof on the last one. Cosine over sine is definitely cotangent squared. And then 1 over sine. Oh my goodness, guys, I'm so sorry. That's cosecant squared. I'm trying to go so fast. Okay, but these are two just coming from the first one. So these are what we call Pythagorean identities. Again, they are used fairly often, so those would be helpful to commit to memory. I'm so sorry, my brain. Okay, so we're trying to use these identities to do one of three things. We're simplifying an expression, we're verifying an identity, or we're solving an equation. Fortunately, we don't have to do all three today, but the first two we're going to attempt. Now, when we're simplifying, it's challenging because there are no set steps, right? That makes this process pretty challenging, especially when you're going about it for the first time. The best way, and really only way to hone your skills to get good at this process is to practice. Okay, is to practice, and you don't, again, have to have anything memorized, but you should be able to find something on that list of identities that you can use in the processes or the problems that you're trying to simplify. Now, one guiding principle while you're working is just rewrite. Okay, just staring at it's not going to do you any good. Find something that you can rewrite so that it becomes apparent what identities you can use to try to simplify. Okay, so the whole guiding principle is for rewriting, just make sure you're using substitutions that are coming out of that chart. Okay, so let me show you a couple of examples, and you can see how some of the strategies, algebraic strategies will come into play. So for number one, we're trying to simplify the cosine of theta plus the sine of theta being multiplied by the tangent of theta. Now that's a lot of different trig things going on in there. In general, cosine and sine aren't things that I try to mess with, so I would start by leaving that alone. I would leave alone cosine of theta and sine of theta, and I would rewrite tangent. Tangent I know is the same thing as sine over cosine. So I'm going to change this, and now I have just two different trig functions in my problem instead of three. And then I'm going to actually multiply these two, okay? So this is cosine of theta still, and then this becomes sine times sine. That's sine squared theta over cosine theta. Okay, now if you have two terms that are in your expression, and now one of them's a fraction, you want to try to add those two terms, add those two fractions, and to do that, you need a common denominator. So the denominator of the first fraction is 1, which means if I multiply by a cosine theta and a cosine theta, I can achieve that common denominator. So I end up with cosine squared theta. Go back to my blue, end up with cosine squared theta here, and on this side I have still my sine squared theta, but now those can go together over my common denominator, which was cosine theta. Okay, so now we're one step closer. The only substitution I've used so far was in the beginning, right? I substituted tangent with sine and over cosine. That was one substitution. Then it's algebra, algebra, algebra. Okay, now I'm about to make another substitution, because on the top of this fraction, I know that cosine squared theta plus sine squared theta, that's one of my trig identities. Cosine squared plus sine squared, that's equal to 1. So now I can rewrite this as 1 over the cosine of theta. So I made a substitution. I replaced this with 1. And then I can go one more step here, because 1 over cosine, that's a reciprocal I know. I know that 1 over cosine is the secant. So this whole thing simplifies to the secant of theta. Okay? Terrible, maybe. I don't know if you're seeing me, and I've practiced this a little, so if I went a little fast for you, I'm sorry, but hopefully the more you work through these, the faster you'll get to. And I would say have that reference sheet handy so that you can see these things jumping out at you. Okay, let's try another. I think this one's a little bit tougher. And I don't know why I capitalized the C in cotangent, so just ignore that. All right, so we've got cotangent, sine, cosine. Again, I would probably fix the or substitute the cotangent just so I'm dealing with two trig functions. So cotangent is the same as cosine, and notice we're using x here instead of theta. It doesn't really matter, it's just a variable, and you will see that variable get replaced with all kinds of different things. So cotangent is cosine over sine, and I'm trying to add sine over 1 plus cosine. Okay, so I'm here. Now I only have two trig functions, but again I'm left in this spot where I have two fractions that I want to try to add together. And in order to add fractions, I need a common denominator. So I made one substitution. I swapped out cotangent with sine over cosine, and now it's going to be algebra work from here. So a common denominator. If I multiply this fraction by sine of x, and multiply this fraction by 1 plus cosine of x, then my denominators are going to be the same. They'll both have a sine and a 1 plus cosine. So what that's going to give me in my numerator is 1 cosine x, and then a cosine squared x, and then over here a sine squared x. All that is going to be over my common denominator, which I'm going to leave. I'm going to not distribute. I'm going to leave it as 1 plus cosine x multiplied by sine of x, and hopefully you'll see why in just a second. Okay, so I made one substitution, and then I did some algebra. I got common denominators so that I could add those two fractions. Okay, now that I've added them and made one fraction, I'm going to make another substitution. Here it is again. Cosine squared theta, cosine squared x plus sine squared x. That's one of my Pythagorean identities, that cosine squared plus sine squared is equal to 1. So I'm going to replace that with 1. So I'm looking at the cosine of x plus 1 over that common denominator. And now we can see it, I'm hoping. Okay, I replaced that with 1. And now I have a common factor to the top and bottom of my fraction. Both the top and the bottom have a factor of cosine x plus 1. So now it's algebra, says that I can reduce something that's in common to the top and the bottom. And so that leaves me with 1 over the sine of x. And that's pretty simplified. However, that's a reciprocal, I know. 1 over sine of x is cosecant. So this all is going to simplify to the cosecant of, not theta. We're using x's here. Whoops, giant eraser. Man, hold on. All becomes the cosecant of x. And there you have it. Algebra. I think the algebra is the hardest part in this because we're using algebra on things that look a little strange, but maybe the whole thing's difficult. I don't know. It takes practice, like I said. Okay? So there's a couple, and we're going to work on this some more, but in a different process where we're going to be verifying trig identities. So when we're verifying, what you're given is two sides that they're already saying, hey, these two things are equal. What we want you to do is simplify one side down so that it looks like the other side to verify that they're actually the same. Now there is a couple, not steps again, it's pretty challenging, but there are some guidelines here that help with verifying trig identities. So when you're going to verify, it's best to choose one side. If we can, it's not always possible. We want to try to choose one side to work with and then simplify it. And the more complicated side is generally the best choice because it gives you more options of things to substitute. And the goal is to take that more complicated side and transform it, rewrite it, make substitutions, use some algebra until it looks like the other side. Okay? We will try to apply and substitute in as many trig identities as possible. Okay, use those trig identities. I can't dot my I's there. It may be necessary, again, to combine functions, to add or subtract terms, to factor, to use all that algebra stuff, okay, that we've talked about before. And then when all else fails, if you find yourself stuck, okay, rewrite terms in terms of sine and cosine, if it's possible, if you get stuck. Rewriting things in terms of sine and cosine is helpful. It often leads you to some inspiration, will show you things that you didn't see before. So if you find yourself stuck, that would be a good way to go. Okay, let's try this out. So looking at example 3, we already know that these two sides are equal. That means I can try to take one side and rewrite it and simplify just like I was doing before to get it to look like the other side. And so this time, this looks a little more complicated on the right here than the left. So I'm going to verify this, and since I'm going to work on the left side, from the right side, I'm sorry. I know my left from my right, I promise. I'm going to say that this is verifying from the right. So I'm going to work on the right side, okay? Just because it looks more complicated than the other side. So I'm going to ignore this. I'm just going to try to simplify what I have over here and rewrite it and make substitutions until it looks like this side, okay? So here we go. First, I have 1 over 1 minus cosine plus 1 over 1 plus cosine, two fractions. Now, I don't want to swap out cosine, but I can add two fractions if I get common denominators. So what I'm going to do is get a common denominator, which would be one of each of these terms. So my first fraction, I'm going to multiply by, I'm going to have to rewrite this, so it's going to get to be a mess. I have 1 over 1 minus cosine x. I'm trying to add 1 over 1 plus cosine x. So I'm going to get a common denominator. This one I'm going to multiply by 1 plus cosine x. 1 plus cosine x. This one I'm going to multiply by 1 minus cosine x. 1 minus cosine x. And so now my denominators, they match. Okay? So on the top of the first fraction, I get 1 plus a cosine x, plus in the top of the next fraction, I get 1 and minus cosine x. And in the bottom, I don't always choose to multiply out, but on the bottom, I see conjugates there. And because I see those, I want to multiply, because when I multiply, I end up with squares, and I know squares are useful in some of my identities. So I'm going to actually multiply out the bottoms. When I multiply here, my common denominator, a 1 and a 1 is going to make 1, and then a negative cosine x and a positive cosine x are going to cancel, and then cosine x times cosine x is going to make, or negative, cosine squared x. Okay? So now what we're looking at, on the top of the fraction, the cosine and negative cosine cancel, and I can combine the 1 and the 1 to make 2. So I have 2 on the top. And then on the bottom, I still have this 1 minus cosine squared x, but I have another trig identity. So this trig identity, that's on the front here, let me see if I can find it for you, where I have a cosine squared. So it's the same identity I was using before, but it's not straightforward where I have sine squared and cosine squared. All I have is cosine squared, but we can manipulate this as well. If I wanted to solve for cosine squared here, I would just take the sine squared and subtract it over. So then I could say that cosine squared is equal to 1 minus sine squared. Or the same thing here, I could say that tangent squared is equal to secant squared minus 1. So you can manipulate these to make them work for your benefit. So that's what I'm going to do in that last step. I'm going to say cosine squared is equal to 1 minus sine squared. Okay, so let me go back. Oops, erasing stuff. Let me go back. I have, where am I at? I'm over here. So this becomes, oh, I used it in reverse. We had cosine squared plus sine squared equal to 1. So I actually have 1, oh my gosh. I actually have sine squared x equal to 1 minus cosine squared x. So again, you're still manipulating. I just turned the page and I lost track of where I was. If I subtract this cosine squared over, I have exactly what I see here. So I can replace that with sine squared x. So now, let me clean this up a little bit. Okay, so this becomes 2 over sine squared x, and I substituted cosine squared x with sine squared x, and I think I've got it from here. So this is the same thing as 2 times 1 over sine squared x, right? I can just pull that 2 out, factor that 2 out if I want, and 1 over sine squared, or 1 over sine, is secant. So this is 2 times secant squared x, and that's a substitution as well. I should probably have labeled that in all the others. 1 over sine squared, secant squared. Let me go back because I think I missed a couple. Yep, this is a substitution. 1 over sine is cosecant, and 1 over cosine is secant. Okay? So there's that. I got one more I want to show you. Hopefully this is coming together okay for you. Now if you look at this last one, we're supposed to try to choose a side that looks more complicated. In this case, and this will happen sometimes, the level of complication looks the same on both sides. So I would actually on this one try to simplify both sides down to the same expression. So I won't be able to, I mean, maybe I could, but I don't think I'm going to be able to transform one side to make it look like the other, but I think I could simplify both of them down to the same thing. So if neither side looks any cleaner than the other, then we're going to try to verify by simplifying both sides. So simplify both sides is what we're doing here. Kind of stinks when you have to do that, but that's why I gave an example so you can see that sometimes it's just what we have to do. Alright, so first, tangent squared. That's one of my Pythagorean identities I can substitute out here. I know tangent squared. If I wanted to get this by itself, I could just subtract over the 1. So I can replace tangent squared with secant squared minus 1. So keep my eraser. I'm going to work on this side first over here. So I'm going to say that this is secant squared, and that variable has changed again. That's called alpha. So secant squared alpha, and if you just want to replace it with an x while you're working, totally fine, minus 1. And on the bottom, we have 1 plus the secant of alpha. Okay, how can I simplify? Now, this might not be jumping out at you, but I was kind of hoping because of what we did on the last one that you would see it here. That secant squared alpha minus 1 is a difference of squares, right? Just like if we had x squared minus 4. That's a square, that's a square. This is a square, this is a square. So we can factor this into conjugates. So the top of our fraction is going to factor into a secant alpha plus 1 and a secant alpha minus 1. And on the bottom, we still have a 1 plus the secant of alpha. Well, that's good because the top and the bottom both now have a secant alpha plus 1. So just more algebra here. We can reduce out what we have in common, which allows us to simplify down to the secant of alpha minus 1. So we took the left side and simplified it down to the secant of alpha minus 1. Now I'm going to try to take the other side and simplify it down, hopefully to the same thing, to verify that these two are equal. So now let me take this side. We have 1 minus the cosine of alpha and the cosine of alpha. Now, just off the top of my head here, I don't see anything that I can rewrite. There's no squares in there to give me Pythagorean identities, but I can separate that into two separate fractions. So I can individually divide these things by cosine just to give me somewhere to go. So I'm going to rewrite this as 1 over the cosine of alpha minus the cosine of alpha over the cosine of alpha. So I just separated that out. Instead of 1 minus cosine alpha, separate it into each of those things divided by cosine of alpha, which is good because now again I can reduce this. This fraction becomes a 1. So I'm looking at, there we go, 1 over cosine alpha minus 1. Well, now I can make a substitution. 1 over cosine is precisely the secant. So this becomes the secant of alpha minus 1. So here's a substitution. 1 over cosine becomes secant. So in everything I did here, sorry, I made this substitution, tangent squared became secant squared x minus 1. So two substitutions, one on the one side, one on the other side. Most of this work is algebra work. It's just weird to look at it because we're doing the algebra with trig. Okay, but there it is. I simplified one side down to secant alpha minus 1. I simplified the other side down to the same thing. So that's verified that these two are equal. Okay, so there it is. I put a handful of problems for you to practice on your assignment in Canvas. The last problem on the Canvas assignment is not a required problem. You're going to see it because I put the directions in there. But I just gave you some extra problems that have answers. That way you can practice more if you want to practice. Okay, so I think you've got enough to get going there. Do your best, and as always, if you need some extra help, then just reach out. All right, guys, take care.